Hi everyone. In the previous video, I showed you how we use Greek letters to represent parameters in our model and how we can store those parameters in matrices. One of the reasons for doing that was if you're using the LISREL software to estimate your parameters in a path analysis, then you're going to have to specify these parameters within LISREL. But even if you're not using the LISREL software, it's often helpful to know what the LISREL notation is and the model is so you can communicate with other people. Well, there are other reasons to use this LISREL notation, and that is we sometimes want to specify the actual equations from the model, and that's what we're going to do in this video. So here is the aspiration achievement model with the relevant parameters in the model that we discussed in the previous video. Using these parameters, we can specify two types of formulas. First, I'm going to talk about what are referred to as reduced form equations. For example, in reduced form equations, what we're simply doing is writing out the linear regression equations that you're already familiar with if you know regression. So, for instance, you'll take one endogenous variable, for example, y1, and then you'll write out the regression equation based on what's in the model. So in this case, x1 is predicting y1, so we have a gamma 1,1, which is simply the partial regression weight. Multiply that by x1. x2 is also predicting y1, so we have gamma 1,2 predicting times x2. And then we have an error term for y1, which in the last video I called zeta 1. And this is just a regression equation with two predictors. Then we could do it for y2 as well. And I'm going to start with x1, that's predicting y2. So we have gamma 2,1 times x1 plus gamma 2,2 times x2, but we also have an endogenous variable y1 predicting y2, so we have a beta 2,1 times y1, and then finally the error term, zeta 2. Now I want to note, just because we're calling these gammas and these betas, they're actually interpreted in the same fashion. They're just partial regression weights. We're going to use this reduced form equations shortly to show you how we actually predict values in structural equation modeling in the next video. Now we could also write the equations in matrix form. Now one reason you might want to do that is if in a paper you want to express the equation in matrix form, which is commonly done, you're going to write it in this fashion, where we're going to have a matrix for y, representing the y variables. We're going to have a gamma matrix times an x matrix. We're going to have a B matrix times a Y matrix. And then we're going to have a matrix that contains the errors or zetas. So for instance, for the Y matrix, we have Y1 and Y2. We put all our endogenous variables in a column here. The gamma matrix from the last video is in this case a 2 by 2 because we have two endogenous and two exogenous variables. And so we have gamma 1,1, gamma 2,1, gamma 1,2, and finally gamma 2,2 times an X matrix, which contains x1 and x2. And if you know matrix algebra, you take the rows, turn them, and then you multiply them by x1 and x2. And then we'll have the B matrix. Remember, the diagonals are 0. We have a beta 2,1 and a 0 up here. And we're going to multiply that by a Y matrix, indicate which endogenous variables are predicting which other endogenous variables. We have a y1 and a y2. And then finally, we have a matrix that contains the zetas or the errors, zeta 1 and zeta 2. And so when you write it in matrix form here, and you might want to write it in this fashion here, this is what's underlying it. And when you apply this, what you end up with, what I mean by applying it, when you apply the matrix operations, what you end up with are reduced forms essentially within a matrix. So In the videos coming up next, I'm going to show you how we're going to use these forms to demonstrate how structural equation modeling predicts values in the covariance matrix.